Hello again, welcome back everyone to ptet.chemistry channel. So this is a continuation of topic 1, which is on mole calculation and stoichiometry. So this is a 5-question part series from 16 to 20. So this question is about reacting volumes of gases. They're quite common in multiple choice questions, but could easily be a whole theory paper kind of questions. So this is about a hydrocarbon. If you watch my other concept development videos, you will have known where I got this equation from. So this is a general equations to show the combustion of complete combustion of a hydrocarbon. It's balanced in terms of algebra. If you have a CXHY, you can start by balancing off the XCO2, and you can start by thinking the hydrogen there will give you the hydrogen atom here. So this will give you Y number of hydrogen atoms. If you total out the number of oxygen atoms on the left, you divide by 2, you will get this number, this expression in front of this oxygen molecule in order to balance this equation in terms of algebra. Alright, so it doesn't just appear by magic, okay? But it's going to be important in this in the context of this equation, because we are going to have to compare mole ratio, where 1 mole is to this however mole this is, to give you X mole of CO2. I wouldn't necessarily compare this because this is water. It's a liquid at room temperature and pressure, okay? So we talk about reacting volume of a gas can be related to the volume of a gas and the molar volume of a gas. This is a constant. So that means the volume of a gas, the volume ratio of gases is going to be equal to the the mole ratio of the gases. Alright, so the volume at start, so it's very important to have a good bookkeeping, no matter how messy you are. If you can maintain your bookkeeping, make sure it's clear to other people, not just you, yeah? So 10 cm cube of the hydrocarbon, I'm not going to write the unit throughout, even though it's important, it's implied in the question. You burn with 70 cm cube oxygen, which is an excess, and then the volume at the end, you have 30 cm cube of carbon dioxide, you have 20 cm cube, this is unreacted. Okay, so the question is how much has reacted. You see, volume reacted. It's very important that you specify reacted. Why? Because whatever that has reacted will form whatever has gone to form the product, you see. So that's why it's important there. Okay, because the oxygen is in excess, so all of these would have reacted. The hydrocarbon would have reacted in excess oxygen. So you started with 70 cm cube oxygen, you end up with 20, so you must have reacted 50 cm cube. Okay, the volume formed is going to be 30 cm cube. So the volume ratio based on equation, your equation shows the reactants reacted, whatever they reacted, to give you whatever that form, Alright, so that's why I can compare these 3 volumes together, but not the original 70 cm cube or the 20 cm cube, because that was not what has reacted in the equation, and this will give you the whatever that has been formed in the equation. There is volume ratio is equal to the mole ratio. These are mole ratio, 1 is to that. So I want the simplest ratio. So the mole ratio, you would divide by 10 throughout. Why we divide by 10? Because we want to get 1. Why do we want to get 1? Because it's 1 in front here. So to compare coefficient, you need that to be 1. And the 50 divided by 10 will give you 5. And 30 divided by 10 will give you 3. So what do we have? So we know that x is equal to 3 because, well, the number in front there represents the mole, right? So we get it to be 1 is to 3, so x must be 3. And then x plus y over 4 equal to 5. So y over 4 equal to 5 minus x, there's 5 minus 3. Y over 4 equal to 2, y is equal to 8. Therefore, CXHY is C3H8. And you know this is a valid alkane because you will have done CnH2n plus 2, which is an alkane general formula from your GCSE or from your O-level. Alright, so C3H8. There's the propane there. Okay, moving on to the next question. So it's a similar kind of A by question earlier in one of the questions. Probably not in this video, but earlier. But it's slightly different because it's asking for the total mole of nitrogen gas in total. You see, this is the reaction 1, this is reaction 2. Reaction 1 produce N2, reaction 2 produce N2. So there are two reactions that produce N2, so you have to work out the total mole of nitrogen from the two different reactions when, well, actually it's when 1 mole of sodium azide decomposes. The sodium azide decomposes to give you sodium and nitrogen gas, okay, but the sodium reacts further with the sodium nitrate to give you even more nitrogen gas, so you need to be careful. Yeah, I'm just thinking what's the best way to think about doing this. Okay, I think I've got an idea. First reaction, the first reaction is probably the easier one. So the mole of nitrogen is to the mole of NaN3. They purposely give you 1 mole of sodium azide already, so I don't need to work in mass or whatever. I am already given in sodium azide. This is from the balance equation. 3 mole of nitrogen is produced from 2 mole of sodium azide. 3 mole of nitrogen is produced from 2 mole of sodium azide. Okay, on the right hand side is the actual. I don't need the volume, I need the mole of N2 actually produced, okay, divided by the mole of sodium azide that actually reacted, which is 1 mole, okay, when 1 mole of it decomposed. Therefore, the mole of N2 from first reaction is just 3/2 mole, which is just 1.5. So that's equal to 1.5 mole. Okay, how about the second reaction? Second reaction is actually the tricky one, because this first reaction gives you the sodium and the sodium reacts further. People don't like it because you see 2 sodium, 10 sodium. In reality, all the sodium here come from all the sodium there. So what I'm going to show you is something about comparing mole ratio. So NaN3, it gives you the Na. Why am I talking about the Na? Because the sodium is the common factor in both equations, alright? That will relate to the N2 from the second reaction. I don't want to look at the N2 from the first reaction anymore because I already found out what it was. I want to find out the mole of nitrogen there. Without working out the mole of Na, I'm going to use mole ratio to skip that part here. So 2 mole of NaN3 give me 2 mole of sodium. That is from the first equation. Okay, so from the second equation, 10 mole of sodium give me 1 mole of nitrogen. 10 mole of sodium give me 1 mole of nitrogen. Now you have a dilemma. This is 2 and 10. They are not the same. Therefore, you cannot combine them together. So you need to multiply this by 5 throughout, because the LCM of 2 and 10, if you do it, is 10. It's 2 and 5. 2 times 5, which is 10. So you need to multiply this by 5, that will give you 10. Multiply this by 5, that will give you 10. Bring that down, and bring that down. The 1 doesn't change. Now both of them become 10 and 10, so I can just equate them as 10. And because when that becomes 10 by multiplying by 5, I have to do the same on the right hand side. So 10 is to 10 is the same as 2 is to 2, which is the same as 1 is to 1. Guess what? I have the mole ratio of the NaN3 and N2. So the mole of N2 from second reaction over the mole of NaN3 is going to be 1 is to 10. So that is from the balance equation. 1 mole of N2 in the second reaction is obtained from 10 mole of NaN3 in the first reaction. On the right hand side is going to be the actual number of mole. So what happened is there's 1 mole of sodium azide that actually decomposed. So the actual number of mole of sodium azide actually decomposed is 1. So the mole of N2 second reaction actual, okay, I'm just writing gibberish now, is going to be 1 times 1 over 10, which is 0.1 mole. You produce 1.5 mole earlier from the first reaction, and you further produce 0.1 mole from the second reaction. So guess what? So altogether, total mole of N2 is going to be 1.5 mole from the first reaction, 0.1 mole from the second reaction. So 1.5 plus 0.1 mole, which is 1.6 mole. Okay, So multiple choice are always a bit tricky if you don't know what you're doing. Yeah, it seems a bit long. I could have cut it shorter if I work a lot faster, but I would have cut down a lot of my explanations, which might not make sense then. Okay. In this question 18, so I had to edit this part of the video, so a viewer, one of you guys, actually spotted a mistake. So I thought instead of letting the mistake slide, instead of, you know, just putting out an addendum image for corrections and stuff, I might as well just re-edit the video and try to explain it correctly in this version. Okay, so what do we have here? We have this inorganic ammonium cyanate. So the only product of this reaction was organic urea. So in the absence of A, that means you are not introducing oxygen. Nitrogen in the A is the one that's unlikely to react because of very strong activation energy for that nitrogen to react. So just by heating up in the absence of A, you don't have any oxygen, which means ammonium cyanate is going to give you all of this urea, which means all of this urea come from ammonium cyanate. So if we have ammonium cyanate, it's an ionic compound, and what we're going to get is we're going to get this simple molecular structure. So this is a covalent molecule, so it's a simple covalent molecule. There's definitely a change in structure and bonding. But what is going to happen is you have conservation of mass, which means everything on the left will goes to everything on the right. In the absence of oxygen, in the absence of air, there's no other product. If we look at ammonium, there's NH4 plus. What do we have here? We have CO, we have 2 nitrogens, and we have 4 hydrogens. So 2 nitrogen and 4 hydrogens. I can further simplify this if I want to, in order to mimic the idea that I have NH4 plus. And we take away 1 nitrogen, we take away 4 hydrogen. We're going to end up with CO, and then N, and that is the balance. There's the outstanding number of atoms, and then because I have one of these, 1 times NH4 plus to represent the 1 times NH4 plus, which means this one must have the exact same charge but opposite charge. So I mean you say it must be a -1 charge, which means the only correct answer must be option A and not what I had previously cutted in the older version of this particular tutorial video where I did this question incorrectly. So thank you to whoever actually spotted the mistake, and do let me know if you spot any other mistakes in my work. All right. Well, I hope that helps. Next question. It's another balancing question kind of thing. So they want how many moles of oxygen to burn 1 mole of lead tetraethyl. So C2H5 is basically CH2CH3. You learn from O-level organic chemistry. That is called ethyl. You have 4 of them. That's why it's called tetraethyl. Each of them is -1 oxidation state. Well, each of the is basically Pb4 plus and C2H4 minus. That's why you get that a compound there. All right. So you get PbC2H5 oops, sorry. You burn in oxygen, so you need to add oxygen, and you will get PbO, lead 2 oxide, Pb2 plus O2 minus. The LCM of 2 is just 1, and you know, just need 1 of these and 1 of these. That's why it's just 1 PbO, yeah. As in basically it's just Pb1O1, which is PbO. Gonna get CO2 and H2O. The Pb and Pb balance out 1 and 1, and besides you only want 1 here because you know 1 mole of lead tetraethyl then. There are 8 carbon, 2 carbon times 4, 2 times 4 is 8, so you need 8 CO2, oops. You need 8 CO2. And then 5 times 4 is 20 hydrogen. So you need 20 hydrogen atoms. You cannot change the number here. To get to 20, you need 10 of the H2O. So now it's just the oxygen that's your problem. So you get 1 oxygen. And you get 16 oxygen there because 8 times 2. And you get 10 times 1, which is 10. And that will give you 27 oxygen. Careful, there is oxygen atoms. And you have oxygen molecule here. So what you actually have is 27/2. Because 27/2 times 2 give you 27 oxygen atoms, which balance out whatever is on the right. 27/2 is actually 13.5. So this is there to confuse people who thought they have got it when in fact you haven't got it if you didn't think about the molecule, because it's not an atom at room temperature and pressure. So think about your situation very well. What is atom and what is molecule? This is the last question of this 5 question series on mole calculations. So this involves gas reacting with aqueous solution. So we needed to dispose of 0.02 mole of N2O4. We have information on that, which is 0.02 mole. We want to find the volume there. So we need to set up our fractions. So I put the NaOH on top. So 2 mole of NaOH reacts with 1 mole of N2O4. Based on the balance equation there, 2 mole of that react with 1 mole of that. On the right hand side, I'll put in the actual amount that reacted. This is from the balance equation. This is on this side will be for the actual amount. All right. So 0.02 mole of the N2O4 actually reacted, and you know this is 0.5 mole per dm cube, and therefore you will multiply by the volume of NaOH times 10 to the minus 3, because you want to convert that into dm cube, because each of these is given as cm cube. So I want the volume in cm cube, convert that to dm cube before I multiply by mole per dm cube. So mole per dm cube times dm cube will give me mole on top. 0.02 mole at the bottom is a mole ratio. It's a mole ratio. It's a mole ratio. Rearrange that, and you get the volume of NaOH being that. Okay. So I moved the 0.02 up there. I moved the 0.5 and the 10 to the minus 3 down there, while keeping the volume of NaOH as the subject, which I have, just reversed the order in my algebraic expression. So I hope you can see through that mathematical step. If you can't, then just do one more step, I guess, and whatever it takes to make it clear to you. All right. So I got 80 cm cube as my expression. So there's 80 cm cube there. Let me just double check my answer, because you never know, sometimes I'm trigger happy on my calculator, and yeah, so I got 80 cm cube again. So yeah, nice and easy then. So that's it for this video. 5 question series, as I said. And I'll see you in the next video. Before I forget, and before you forget, so do subscribe to the channel if you haven't, and then share the words to your friends, your class chat, your teachers, whoever else you think might have interest in these O-level and A-level chemistry content that I cover on my channel. Okay, so thank you for watching.